We should record it, at least the presentation, or do you prefer to stop it? Sorry,
Yeah, okay.
It's up to me.
We'll stop, I mean, when the presentation finishes. Okay,
yeah.
So this is the master thesis defense by Álvaro Luque Sánchez with the title Big Data, Memes, Information Diffusion in Online Social Networks and Opinion Dynamics. And the jury is formed by Dr. Sandro Meloni, that is the secretary, Dr. Jose Ramasco, who is the advisor, and myself acting as president. So this is your time, Alvaro, and as we say normally, we ask for these presentations that you do not go beyond or much beyond 20 minutes. So 21 is okay, but I mean, try to fit in this time slot. So,
may I start?
Yes.
Okay, so good afternoon, everyone. I am Álvaro, and I'm going to present my master thesis for this year. First, you can see here the outline of the presentation. We will do a brief introduction on online social networks and the specific example of Twitter, which we have analyzed in this work. Then we're going to explain the methodology that we have followed for this work, the basics, and our objectives for the results. Then we will delve into the results, where three main sections will be analyzed: the filtering and data results, network structure, and the topic analysis, which is the main part of the work. Then we will discuss a bit about conclusions and future work that can be done after this work. So first, online social networks are a very common thing these days. We are surrounded by them, like Twitter, YouTube, Facebook, actually any kind you can imagine. And each one has different motivations and target audiences, searching for example, music sharing, video sharing, or more microblogging like Twitter. For researchers, online social networks are a very important source of data because of their volume of users mainly, and because they allow for modeling human interactions or information spreading very easily. Since typically we account for pairwise interactions in online social networks, like following a person or being followed back, network theory is a very suitable framework for this and can extract very useful information from the data we're analyzing. For example, we can talk about the topological properties of some of these networks, like the degree distribution, the clustering, the average path length, which tend to be important. But in the context of social networks, like the online ones, a very big topic is community structure, since as we already know, in social context, the community structure of networks plays a very big role, since our experience of society, we are always falling into groups of friends, of acquaintances in high schools or university or whatever. And then it is also very important to study the dynamical aspects of these networks, from the mechanisms that motivate the network growth, like, for example, triadic closure or homophily, and then to potentially simulate epidemic spreading on information cascade models, which are more dynamical processes that take place on the network that we build. Last, about these online social networks, typically they have a very large volume of data associated to them, and constantly new techniques for sampling users or sampling connections between users are being developed to alleviate a bit this computational cost, and working with a statistically significant part of the network from which we can extract similar results. Examples of these are just simply randomly deleting nodes or edges, or more sophisticated techniques like random walks over the networks, which relate to Metropolis Hastings algorithm, to choose which parts of the network are really important. Then Twitter is a microblogging online social network which has hundreds of millions of users. I'm sure everyone here has used it. And it comports an enormous volume of posts per year due to the popularity. In Twitter, there are many ways to interact with other users, but in this case, we will focus on replies from one user to another, which will establish directed relations between users, and we will add a weighted character to these connections by counting how many times this directed interaction takes place. The main goal is then to detect communities and analyze the use of hashtags within them. Hashtags in Twitter are a very big thing because they allow to condensate information on very short topics that can be followed by other users or shared, or they allow for a very versatile type of conversation. In this work, we have used data from 8 years of observations from Spain, Great Britain, and Netherlands to study the hashtag use and behavior inside communities of the network. Let's jump to the methodology. First, as a brief description of the database, we were given data files, one per year and country, which contains replies of users to others. These replies have certain attributes, like the user IDs, which are hashed versions of the real usernames for anonymity, the text, which is just the content of the tweet, time and location information. From all these, the most important are user IDs and location, because we'll use it later for filtering. I will explain it in a second. And it's important to know that location information may appear in two forms, rather as precise location, like an exact GPS point, or a bit more weak information, which is just a bounding box formed by 4 points, which contains the users, but there is no more information about where this user is. Then to build a network, we just need an adjacency list of the directed relations between one user and another, and the weight that this connection has. But as I said, by counting how many tweets are directed from user 1 to user 2. We will build one network per country by aggregating the 8 years of data. One thing that we must have into account is that Twitter and any real database has errors, in this case of online social networks, there are bots included in the database, which their behavior is rather simple to study, and we have to take them out. So for this, we will explain how the filtering was done for our case. We developed 2 kinds of filters. First, to eliminate users that tweet very rapidly, like their count of tweets per hour is beyond a certain threshold that we decided that was more or less logical. Then another strange behavior is when a user tweets consecutively from places that are realistically too far from each other. For example, if to post one tweet at one location and certain time, and then another in another location and certain time, we can calculate the relative speed by calculating the distance between the points and the time span between the tweets. And realistically, if this speed exceeds, I don't know, 1,000, 2,000 kilometers per hour, then we know that this is not a normal user behavior and there's something strange going on here. So these are the 2 main strategies to remove bots from our database, which also eliminated some abnormal user behavior, like people whose activity period was very short and they tweeted a low amount of time, so the count of tweets per hour was very high. And then for the distances, as we said, we need to define a quote-unquote new way of calculating the distances, because we have bounding boxes involved. And as you can see in the figures here, what we did is when a bounding box is involved, either 1 point and a bounding box or 2 bounding boxes, then the distance between the objects is calculated from the points that intersect the segment that unites either the center of 2 bounding boxes or the GPS point and the bounding box. As you can see here in the figures, for example, here, the distance between A and the bounding box would be the distance between A and the point I, here in red. And similarly here, the distance would be taken as the distance between I1 and I2. This is for the filtering. And now, this has moved. I'm sorry about this. This LaTeX has moved a bit. In any case, here we will explain the topic analysis that we conducted and how we think the results are going to show up. First, we will base our analysis in two hypotheses. Hypothesis A would be that there exists a sublinear growth of the number of unique hashtags as community size increases, similarly to Heap's law in written text. So Heap's law actually relates the number of unique words or the size of the vocabulary with the total number of words in a written text. But actually, in our case, we expect that the total number of hashtags, which would be the analogous quantity to the total number of words, is expected to be directly proportional to community size, since by aggregating more users, we expect more activity and more hashtags shared. We will study this in detail. And then the other hypothesis, hypothesis B, is that there exists a boundary at around 150 members that distinguishes between small and big groups. This is motivated by anthropological studies that we will comment in the next slide. First, for each country, we need a master dictionary which preserves an order of counting hashtags, because later we will use hashtag counts to be considered as vectors. So we need some kind of consistency in which order we place the hashtags. Of course, it is not important in which order they are arranged. Actually, we did by order of apparition in the database, but we need to have an order for the vectorial operations to make some sense. Then we will build a hashtag count array in which each row will represent a community and each column will represent a specific hashtag. We don't need to know the value of the hashtag, meaning the string of text. We only need to know which is the position in the array. For this array, the number of columns, which is the total number of unique hashtags for a given country, is denoted by NH prime, uppercase. And then for each community or each row of the array, NH represents the number of unique hashtags, meaning the number of non-zero components in this row. And then NH uppercase is the total number of hashtags, which is just the sum of the components of a given row, which is just a vector. And this is very handy for computation later. So following our hypothesis, if hypothesis A applies, meaning that there exists this sublinear growth on the number of unique hashtags, then the number of unique hashtags follows a law of this kind, with the exponent being smaller than 1. Meaning that if we divide the number of unique hashtags by the community size, which would represent the number of unique hashtags per user, this should be a decaying quantity with community size. Then hypothesis B is motivated, as I said, by these studies of Robert Dunbar relating average primate brain size with typical social group size. There was a value extrapolated of around 150 stable social relationships for humans. Also, if hypothesis B apply, we can expect the following behavior. Small groups should play the role of real-life groups, close groups of friends, which are associated with a bigger variety of unique hashtags, which are repeated less. These are, for example, when you discuss crazy ideas with your friends, and big groups, in contrast, should be more focused towards following a certain topic or a certain amount of topics. To quantify the repetition, we define this repetition rate, which is just the number of total hashtags used for a community divided by the number of unique hashtags that they have. And then we will compute the cosine similarity, as I said, between vectors representing the rows of this hashtag count array, so that we can quantify how similar two communities may be. And we will analyze this as a function of community size as well. Let's jump into the results. Here we have the preliminary results, which are more related to the database itself. Here we can see the number of uses that the filters eliminated. As you can see, the location filter eliminated more users than the other one, but still the percentage of total users that were eliminated was not large, and we can discuss about this a lot of things. And then we have the number of total tweets that were analyzed during the 8 years for Spain and Netherlands. Sorry, I forgot to say this. The results of Great Britain were not clear and were not presentative. And then we have in the second column, we have the number of tweets with hashtags out of those total tweets and the percentage that they are. Then finally, in the last column, we have the total unique hashtags for each country. In this figure here, what we can see is, given a tweet that contains hashtags, what is the probability to find H hashtags in said tweet? This is just a quick study to see that the average number of hashtags per tweet is very close to 1, because the curve decays very rapidly, which is also expected. Then let's jump to the network structure. In this table, we have the basic properties of the network, namely the number of nodes, the number of connections. The last column represents the average degree, while the third column represents the average number of connections without taking into account the degree, the weight, sorry. This was for just informatively. And we can see that the networks are pretty big, especially for Spain. But still the mean degree without weight is kept low. In this figure here, we can see the in-degree distribution for the two networks. In orange, we have Spain, and in blue, we have Netherlands. We can see, well, it is more or less sensitive to assume that there is a power law mechanism here, because the CDF is kind of straight. So we did a maximum likelihood estimation of the exponent, which is much more precise than the typical linear least squares fitting, which does not capture what we see in the figure, which is clearly probably as a result of the difference in size of the networks. The exponent of the supposed power law must be bigger for Netherlands than for Spain, which is captured here in the maximum likelihood part of the table. This is not the main result, so we'll just quickly see also the out-degree distribution. Here we can see that we completely lose the power law, or at least the pure power law behavior. Maybe it resembles more a log normal or a Pareto log normal distribution. In contrast, we can see for the weights that the weight distribution are kind of similar between the two countries, except for this region. Seeing the CDF is much better. Between the weight between 10 and 1000, we see that there is a separation, but then the curves are pretty similar, which is also an interesting fact. And then working towards the topical analysis, we need to run community detection methods. We run two actually for the work, both Louvain method and InfoMap. But InfoMap yielded very bad results, not very consistent, so they are not presented here. They are in the long document. We'll see now the community size distribution for the Louvain communities. We can see that as well. These two curves are remarkably similar, and the CDF as well, of course. As I commented before, we will consider the size of 150 to be very important, and we can see that it is already quite difficult to find communities of more than 150 people because the PDF is quite steep, so there is a relatively low probability, and we will explain how we have solved this issue more or less. So for the topical analysis, since there were a lot of communities found in these big networks, we were forced to take a sample of them to study them. Since as I have commented before, the structure of the community size distribution is very heterogeneous. If we want to have statistics about big communities, we have developed a new method for sampling this. Not new, but not just uniform sampling, because then we will have no. So we take the 1% of the total communities found, And then we try to take this quantity from both small and big communities, separated by this 150 boundary. We can see that for the case of Louvain, big communities represented much less than the 1% of the total community, so we had to take them all to have decent statistics. Furthermore, the heterogeneity of data, meaning we may have a big community that has 0 hashtags and then another that has 1,000. So we treated the size as bins and then aggregated a lot of data points inside them and treated them as a statistical distribution. So we'll be seeing a lot of violin plots and some other plots that I'll explain later. So the first results come from the number of unique hashtags as a function of community size, just divided by this 150 mark. We can see that for small communities, smaller than 150, the distributions are very, very peaked around low values, around 1, 2, 5. You can see the median here as a white dot, and the distributions are pretty close to that value. Meanwhile, for big communities, we can see that the distributions stretch a lot, and the interquartile range, which is described by the boxes, is much larger. And also the medians are clearly higher than in the smaller case. To study this with a bit more resolution, we now change to binning the size. We put it in logarithmic to see orders of magnitude. This is decimal logarithm, and you can see that this trend is indeed there. And here in the vertical axis we have the number of unique hashtags. There is a trend of growing NH lowercase as community size increases. And if we were to take these first points until here, which marks sizes of around 1,000 people, we can see we can do a fit of these points to obtain a slope of 0.7, which is in agreement with what we said, that this should have a exponent smaller than 1. Remember that this is in logarithmic scale, although the scale of the graphics is linear. So it means that the exponent of this law is around 0.7. If we were to compare, as we said that the number of total hashtags and the size should be directly proportional, we also try to do this plot as respect to NH uppercase, which is the total number of tweets. And we can see that there is also a trend, but the exponent is slightly different. But it's good because there's both smaller than 1, and this difference is a result of there is not a one-to-one correspondence in number of total hashtags and community size. I didn't explain it, but these plots, the points are actually the median of the distributions in each bin, and the errors correspond to the interquartile range, as in the violin plot, but this was clearer than the violin plot in this case. So now what we want to look at is the repetition rate of the communities, and we can see that the results that we expected are here. Being smaller communities have a very low repetition rate, around 1, which is the lowest value, and the distributions are also peaked around this value. While when we go to big groups, the repetition rate is a bit higher. We can see that the medians are not much higher than in the case of unique hashtags, but indeed the distributions change shape, and higher repetition rates are expected for big groups. And lastly, as we commented, if we compute the cosine similarity following the ideas of hypothesis B, if small groups tend to have a wider variety of themes, we expect bigger overlap between the vectors of one community and another if both have a small size, while in the case of big communities, they have a lower number of hashtags per user. The distribution is more peaked, the distribution of hashtags is more peaked around certain topics, which are the ones that they repeat the most. So we expect more zeros in this value of similarity, or at least more low values of the similarity. Well, you have here the formula for the cosine similarity is just the cosine of the angle that they form with the dot product. And to say, take into account that this thing, if you have n communities, you have to do the order of n squared operations to evaluate all the possibilities. So this is the main drawback and the main responsible for having to do the sampling of communities. You can see here the results for the Louvain communities of the both countries. As we expected, the small pairs, which are pairs in which the two communities are small, the mix is where one is small and the other is big, and the big pair is where the two communities are big. And as you can see here, there is a lower proportion of values between 0 and 0.1 for the small pairs, but as the value of the cosine similarity gets bigger, the proportion of small pairs that have this value of the similarity also increases. So as we expected, the cosine similarity is higher for smaller groups because they have, relative to their size, they have a much broader distribution of tweets, a big variety of hashtags that they manage. So these were the results.
Sorry, Alvaro, can you wrap up? I mean, conclude.
Yes, only the conclusions.
Already 25 minutes.
Yes, sorry. Then the conclusions very quickly. The key aspect of this work is an efficient implementation because no specific tools for big data were used, like Dask or SQL database, which would have helped a lot in the calculation of the different quantities. Also better data preprocessing, mainly lemmatization of hashtags, since we are handling with a lot of hashtags that have very similar meanings and that can be grouped into one. This would reduce the amount of zero similarity groups because, of course, if two communities use a slightly different hashtag, this method doesn't count this as a similarity. The improved filtering, which is just trying to eliminate more uses, but this was kind of okay. And also dedicated algorithms and heuristics to improve the computation time. Then also we suggest a suitability study of the community detection methods because, as we said, InfoMap was not suitable, and we tried also Oslom, but it was too computationally expensive, and we declined it. And then, despite the difficulties, we can say that both Heap's law and the Dunbar's typical division apply in this case, although the statistics of the results may be improved. As a last thing, the future work we propose is to build a community of the networks where the weights of the links are related to the similarity, and then study a propagation model of certain messages that try to enter the communities, depending on the similarity that the message itself has with the community. So there would be an effective parameter for each community. Then this is a very important model, and one can measure, for example, the virality of one hashtag, one message that is especially easy to propagate in this kind of network. And this is a novel approach because all that we have saw in the literature computes or simulates dynamical processes at user level. Well, in this case, we are doing this at community level, which hasn't been explored thoroughly. So that is all, and thank you, and I'm ready for your questions. Sorry for the time.